For the introduction, active filters are essential power electronic devices designed to improve the quality and reliability of power grids. They address various power quality issues, including harmonics, voltage imbalance, flicker, voltage sags, swells, and low frequency oscillation. These filters also play a crucial role in integrating renewable energy sources such as solar, wind, and biomass by acting as interface and enabling the smooth adoption of distributed generation and microgrids. Active filter can be classified into three main types. Shunt filters, which is focused on current-based compensation; series filters, which address voltage-regulated issues; and hybrid filters, which combine benefits of both. Their applications span across industries, including harmonic compensation in steel mills, voltage regulation in data centers, power factor correction in electric vehicles, and islanding detection in microgrids. With advancement in high-power semiconductor devices, digital processors, and sophisticated algorithms, active filters have become indispensable in enhancing energy efficiency and ensuring power system stability. For the calculation, it has been divided to four pass filter. There is two of them is high pass filter and two of them is low pass filter. From there, we can calculate the voltage gain. There is 3 minus 1 is equal to 2. So 2 is our voltage gain. So let's assume that our RA is 20k. From there, we can use the non-inverting formula to calculate to find the RF that we need. For the frequency, it has been given 500 Hz. For the high pass filter, let's assume the R is 1.5k and the low pass filter is 2.5k. Using the frequency formula 1 over 2 pi RC, we can calculate to find the C capacitance that we need. For the high pass filter, we can get 0.2.1 microfarad, and for the low pass filter, we get 12.73 nanofarad. Then total gain, the total gain that we got is 90 is equal to 16 multiplied by A5. To find the A5, just change it to divide, so it's A5 is equal to 90 divided by 16. We can get A5 is equal to 5.625. Again, using the non-inverting formula, we can calculate the RF by changing the total gain. 5.625 is equal to 1 plus RF over RA. From there, we can find our RF. With RA value is 2k, that makes it the RF value is 9.25k. The mid gain decibels, using the formula again, 20 log A, just changing the A total to the value, 20 log 19 is equal to 39.08 dB. Lastly, to search the center frequency, it is square root FH multiplied by FL. We already got the frequency FH. Just put in the 5k that we got. The center frequency it will be equal to 1581 Hz.
Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hafiz bin Abdullah. Today, I will presenting our group circuit design which focus for fourth order band pass filter. Here is the schematic of our circuit design. The circuit consign the two high pass filter and two low pass filter and non-inverting amplifier for signal amplification. The goal to find the specific range and amplify resulting signal using OTS. The first stage of the circuit is the high pass filter using R1 and R2 resistor and C1 and C2 capacitor along with operational amplifier. The second high pass filter consisting of resistor R3 and capacitor C3 and RF2 RA2. So for the next stage is low pass filter consisting of R4 and R5 resistor and C4 and C5 capacitor. And the second low pass filter is using R6 resistor and C6 capacitor. For the final stage of the circuit is using non-inverting amplifier. The gain amplifier is determined by the feedback resistor RF5 and RA5. So after we design the circuit, we need to run this circuit to get the graph for our gain and low tap of frequency and high pass frequency. When we run the circuit, the graph will show. So the graph will represent the frequency response of our circuit. So for the x-axis represent the frequency of the input signal while the y-axis show the gain. So to find mid gain, we need to find the higher of gain, which is 39.1 dB. After that, we need to find low high pass frequency, which is 502, and the gain we get 36.1. So to find high cut frequency, we also use the same value gain, and we will get 4.96K. That's all from me. Thank you.
My name is Muhammad Ali Isa. My mother number is AE210002. The table shows the given values and measuring values for various parameters of a project. The parameters including mid-gain, low frequencies cutoff, and high frequency cutoff. Mid-gain given value is 39.1 dB, measuring value 36.1 dB. So low frequency cutoff given value 500 and measured value is 502. High frequency cutoff we have given value 5k and we got a measured value it's 4.96k. Conclusion: the study successfully designed, simulated, and analyzed fourth-order active bandpass filter using a Butterworth configuration targeting a frequency range of 500 Hz to 5 kHz. The theoretical calculations were validated through simulation in a Proteus professional, showing strong agreement with the predicted performance, including a stable mid-band gain of 90 and attenuation rates of 80 dB decade outside the bass band. The filter's excellent frequency selectivity makes it suitable for application in audio processing, communication system, and biomedical devices. The analysis also considered practical factors like component tolerance and operational amplifier, non-idealities, which had negligible effects on performance overall. The study highlights the significance of active filters in modern electronics, particularly in areas like renewable energy, integration, and smart grid.